I guess the way I conceptualize it, there are now three models of computation. There's quantum computing, there's traditional classical algorithms, and there's deep learning, LLMs, AI. These are different classes of computational structures that are useful for different things. We in Phasecraft will leverage the best of all of them. So there's stuff we do where we're using classical algorithms together with neural network deep learning, together with quantum computing, and harnessing the best of all three. So they're complementary. The things that deep AI is good at are not the things that quantum computers are likely to be good at anyway, and vice versa.
What if the timeline to quantum advantage wasn't just about qubit counts? It turns out clever mathematics and algorithmic breakthroughs are slashing the physical qubit requirements by orders of magnitude. Find out how we might have already bought a decade worth of hardware development through pure software innovation in this episode of the Post-Quantum World. I'm your host, Konstantinos Karagiannis. I lead quantum computing services at Protiviti, where we're helping companies prepare for the benefits and threats of this exploding field. I hope you'll join each episode as we explore the technology and business impacts of this post-quantum era. Our guest today is the co-founder and CTO of Phasecraft, Toby Cubitt. Welcome to the show.
Hi, thanks a lot for having me.
And for those listening or watching, it is Cubitt. It's just spelled C-U-B-I-T-T. So I'm sure you hear a lot in this industry as a result, right?
Ever since I started a PhD in this longer ago than I want to remember.
Yeah. My real last name is Algorithm, but I changed it to Graduate.
I genuinely didn't change my name. If you Google my personal web page, there's an very old blog post explaining, slightly jokingly explaining the relation my name and which there isn't any, but it's a very nice coincidence. Did I choose the field because of my name? Who knows what psychological effects it played.
Yeah, I get. Or you could have been a biblical scholar because the spelling is a little closer to that. Yeah,
that's right.
Yeah, you could have found the lost ark. So why don't we start with you just telling our listeners a little bit about Phasecraft in case they haven't heard of your company?
Sure. So Phasecraft's a quantum algorithms company. We founded Phasecraft, myself, Ashley Montanaro, John Morton, the co-founders, 6 years ago now, and with a mission of getting useful applications running on real quantum hardware without waiting 20 years or hopefully even 10 years. But really and what we realized is that all three of us had been in academia in quantum computing for 20 years each. And we realized that, it got to the stage where this hardware was, most of my career, quantum hardware was something I could emulate on my laptop better than the real thing. That got to the point that's no longer the case. But there's two things that matter for making a quantum computing industry really take off and become not just a sort of prototype industry or industry in the making, but actually mature. One is you need the hardware to run stuff on. The other thing is you need to be able to run something useful on that hardware. We're in that second business. And because that's very difficult and non-trivial at the moment, a lot of what we do is algorithms research, but very much targeted at real world applications, but doing the clever maths and algorithms to get those real world things onto the actual hardware now.
Yeah. And when we were first planning this episode with you, we were going to stick very much to the idea of the algorithms and what people want to do useful use cases in quantum. Yeah. But it's funny, the last month or so has just been a barrage of papers about algorithmic approaches to cracking cryptography with fewer and fewer and fewer and fewer qubits. So I did want to just quickly ask your opinion on that, because I almost feel like it makes your case for you. Because for a long time, people were just thinking we need, let's say, millions of qubits, and when are we going to get there? But it's this idea where the need for the qubits keeps plummeting now, and the actual physical qubits we have keep rising. So at some point, those two lines are going to cross. So
this is absolutely right. Yeah. And what we've always said at Phasecraft from the very beginning, and it's not controversial, it's kind of obvious, it's played out this way in the early days of classical computing. The hardware is progressing, and it's progressing steadily. And if you track things back, it's actually kind of doubling number of operations you can do every year or two in a sort of Moore's law type growth. It's fairly steady. It's bumpy, of course. On algorithm side, we're really at the beginning of a whole technology here on the practical side of things. In the same way that classical computing was in the 1950s. There, you can have one idea that will change the timelines by 10 years by just having an idea on the algorithm side that massively reduces what hardware you need before you can run something useful. So the recent story with Shor's algorithm is exactly that playing out. Now, it's usually not one idea. Like that Peter Shaw level breakthroughs come, once a decade or less, but it's the more applied side where there's 5 different clever ideas, each of which knocks off a factor of 10 or 100 off the gate count, off some clever math that lets you not keep track of the entire integer you're factoring, or put all of these things together, do the nitty-gritty hard work of thinking, how am I going to actually implement that in the real world hardware with its constraints or particular architecture? Do all of that together. And you suddenly see like, oh my God, the timelines have changed by like some of the stuff we did in Phasecraft early on. We literally knocked off a factor of 1 million of the best algorithm for simulating the Hubbard model that had at that time. And I think I once just took log 2 of 1 million, and you're talking about a decade of hardware development that now doesn't need to happen to run the algorithm. So the really game changing in terms of how soon will we get to breaking RSA cryptography, simulating strontium vanidates, solving logistics problems for a shipping company that's at a meaningful scale. We can track the timelines at the moment, but an algorithmic breakthrough or a handful of smaller but insignificant ones stacking can change that timeline radically in a way that in some sense the hardware development is a little bit more predictable. And that's what's been happening with Shaw's algorithm. And like people have been doing the hard work and having the clever ideas or putting together known ideas that are in academia and combining them in an applied way, in a clever way, and showing that actually, no, maybe we don't need anywhere near as much as we thought we did. And that's very much the kind of thing that Phasecraft does as well.
Yeah, so that's been getting a lot of attention for obvious reasons, because then it also has this stigma of Q Day. This is our, when those lines cross, it really is Q Day.
That's right.
So I do want to bring attention then to all the work you guys are doing, and that same exact excitement is happening. It might not be getting the same amount of press because we're not worried about the end of the world as a result of what you're doing. For better, probably better. Yeah.
I mean, to talk to you, like the cryptography and breaking cryptography side on a technical level, to some extent, we have the solution already. That post-quantum crypto is a thing. It's actually a very mature field. I'm still very part-time, but I'm still occasionally in my office in UCL. I'm still a professor there in London. Down the corridor in the CS department of people, there's an entire group who work on post-quantum crypto. It's a group's been around for decades. It's NIST has standards. It's not as mature as RSA-based crypto and similar, but it exists. We know what we need to do. Deploying it is not a trivial problem.
Yes,
but it's not a mathematical technical problem. We have a bunch of solutions to it, and there's reasons to believe that those crypto schemes are secure against quantum computers because we understand quantum algorithms well enough to know what is likely to be not within their scope. So in some sense, if you care about your communications being secure for the next, 30 years, you needed to be worrying about quantum computing, already 10 years ago. But these timelines might mean that, you should have been worrying about it 20 years ago, perhaps, and you should be getting on it. On the other hand, we have it, the factoring RSA is, or the other like hidden subgroup-based cryptography schemes are obsolete as soon as people stop using them. I don't trivialize the challenge of deploying that. The other applications where there's a similar story playing out with perhaps less attention is on things where we know that it's not going to be obsoleted, at least on a theoretical perspective. So the classic one, which we do a lot of work on in Phasecraft, is simulating quantum physics. It's Feynman's original 1982 spiel. Feynman was a smart guy. It's kind of annoying that he was right because, it's annoying when someone's right about everything, but nonetheless, he said it 40 plus years ago now.
The universe is quantum, damn it, right?
Yeah.
Basically, was his.
That's right, and you need quantum computer to manage to simulate it efficiently. That is computational chemistry. That is one of my things that I'm very even keener on, which is computational materials modeling. It's also condensed matter on scientific applications, condensed matter theory. But in terms of the commercial world, when you talk about computational chemistry and materials modeling, in terms of applications, you're talking about all modern battery technology, modern photovoltaics, catalyst optimization in almost all industrial processes. All of these things are we use classical computers now, huge supercomputers, to try and model these things, but in a way that it works, it's good, it's useful, but sometimes it gets the answer completely wrong. It's kind of known why. Quantum computers we proved mathematically 1995 that quantum computers can do this efficiently. And we also know that if classical computers can do this task, then every quantum computation can be done classically, which is very unlikely to be the case. So these are known hard tasks on classical computers for well understood reasons. Much better, whereas factoring could be there's a classical factoring algorithm out there. So that's an application with huge ramifications, because once you take materials modeling, chemistry discovery out of the lab and into silicon, maybe, but maybe it's superconducting, or maybe it's ion traps or whatever in Quanto, that will revolutionize all of those areas of industry in the same way that computer simulations have revolutionized other areas of like engineering, building bridges, modeling, building. We have architecture that just couldn't exist without computer modeling these days. We're used to that. That is a completely sort of, it is a society level change in the same way that or I would say almost more profound than breaking RSA crypto, but less, high profile. Then there's the, combinatorial optimization problems. It's the other big area we work in Phasecraft and put effort into on the applied side. We released Mondrian recently, which is a sort of demo version of how much we can speed these problems up, which we can talk about more. Again, these problems it's a different nature. It's not known provably that quantum computers will solve these problems faster than classical. It's not known they can't. The best classical algorithms are all heuristic. The best quantum algorithms are all heuristic. So the proof of the pudding is then to run them, which is challenging, of course, on current hardware, because quantum hardware is incredibly powerful, but also incredibly early stage. But we've shown how, against the best classical algorithms, we should be able to, using a hybrid approach, be able to speed up solving big combinatorial problems by a factor of 100, 1,000, by harnessing kind of the best of both worlds. But combinatorial optimization problems are everywhere. Despite AI and machine learning, most compute cycles are spent on, most are spent on searching or sorting. But other than that, sort of algorithmically, combinatorial optimization is everywhere, from logistics companies, from recommendation systems on which video you should watch next. So the applications are way more diverse than, say, in chemistry and materials. And again, it will be revolutionary if quantum computers can solve those things faster in some cases than our existing methods.
So let's say that 1000x speed up. That's a 1000x speed up over previous quantum approaches, right?
No. So that is a 1000x speed up over classical algorithms.
Okay.
But then you can get into, and the details matter. I'm a scientist. I care about being scientific integrity, honesty, and so I should. I think it's worth try slightly unpacking that. So, if for most combinatorial optimization problems, if you look at that specific problem class and structure, you may be able to design or adapt an existing heuristic algorithm for that and make it extremely fast. So this 1000x is speed up over the best general purpose classical optimization algorithm that hasn't been honed specifically for that problem and tailored to that. Of course, the same applies on the quantum side. If you take the quantum algorithm and hone and tailor it to that particular structure, you also can get a speed up. So it's trying to compare like for like of a black box solution, but taking the best general purpose optimization algorithm that we found empirically for these particular problems and pitting it against the quantum classical hybrid algorithm. So it's 1000x over that.
Okay, so that's why you can't claim advantage, I guess, because in theory you could go into the black box and tweak that, and then.
And also, we can't yet run those algorithms at scale.
At scale, yeah.
Yeah. So you could, at the moment, certainly in Mondrian is a demo. If you want to actually run that in anger, you have to talk to us. The demo version where we can simulate the quantum computation on a classical computer, not very quickly, but that's fine. In the comparison, we've assumed that, but that's of course slower, but you can still do it because the demo is on small enough scale that you can still brute force simulate the quantum mechanics, just slowly.
So for your simulations, I want to ask you a couple of platform questions, I guess. So for the simulations, are you doing pure state vector, or is there anything?
No, it depends on in what domain. So brute force raw state vector is good when you want to just test something numerically first in small scale to you're doing algorithm research development. Mm-hmm. Very quickly you run out of steam on that. We uniquely in Phasecraft have access to all of the world's best quantum computers, and I think we're the only people in the world with access to all of the world's biggest quantum computers. I mean, we're running on Google's Willow chip. We were before they announced the Willow name. We're working with Quantinuum and running on their hardware. We're working with Quiro. We're working with Getty. We're working with IBM, etc. So we are literally running on all the world's best quantum computers. So we test a lot on actual running on big iron stuff, on big iron quantum hardware where you can't simulate it. We also do a whole load of red teaming on the most performant classical heuristic algorithms, which are tensor network-based methods often.
I was going to ask about tensor.
Yep.
I didn't know if you were going to do any of that kind of like approximating with tensors to get more qubits or anything.
We can, or because a lot, for example, if we're looking at simulating many-body quantum physics, the best thing to do that use with the tensor networks is go directly to the problem you're trying to solve and compete directly rather than simulating the quantum computation. We do that as well, but often even more performant is to directly try and solve the physics using tensor networks methods. They're incredibly good. It's tough competition. They're heuristic, but they're very performant. So we try and, we need to know if we're beating those. So we do a lot of work internally on essentially red teaming our own stuff to somehow, in some sense, defeat our own quantum algorithms with heuristic methods. Like, but the tensor network methods are delivering as accurate answers,
they're
even
called
way beyond state
quantum
vector.
Inspired for a reason, not because they're inspired by quantum computing.
That's right. Exactly.
The way that quantum works.
So no, the competition's stiff. The good thing is quantum computing, those are up against an exponential, wall, and an exponential curve quite quickly looks like a wall. You can keep on pushing out the tensor network methods, and people do, and clever people do these, and we have tensor network experts in-house to making sure that we're using the state of the art. We're not necessarily developing those algorithms ourselves, but making sure we're using the latest out of academia to test against. But they do hit up against the exponential growth of Hilbert space ultimately.
Yeah, because you have to be able to contract them.
You have to be able to contract them, or if you do 1 DMPS, the contraction is simple, but then the entanglement growth might mean you lose accuracy very quickly. But it depends on what physical quantity you're trying to compute. Because in the end, you care about, I want to compute the charge drift coefficient of lithium in a cathode material. I don't necessarily need to figure out what the entire quantum state is or have an approximation for everything, just that one quantity. So we have to win on that if it's quantum advantage. So we set us a pretty high bar for what we call quantum advantage in Phasecraft.
So do you use any kind of benchmarking to decide which of these modalities you're going to try a problem on because you have access to all of them?
In terms of the quantum hardware modalities?
Yeah.
That's a really interesting question. So it's a really interesting time to be working in quantum computing technology because it feels to me like the 1950s of classical computing, when you had all kinds of crazy ways of building, say, memory, from mercury delay lines, where you're literally storing bits in like waves on mercury, and then you pick them up at the end with a piezo transducer and freeze them back in to keep them alive, versus drum memory, and like no one knew what the right technology was. And then it got boring because CMOS, MOSFET, transistors took over, silicon, and then all the technology looked the same. We're not in that era. Superconducting circuits are fantastic in some ways and not as good in others. Ion trap quantum computers have very different pros and cons. There are algorithms that on ion trap quantum computers we just can't run because we can't get the shot count. So the clock speed is 1,000 times slower for kind of fundamental physics reasons. So you can't take as many shots, but it's much cleaner. So we might have to design the algorithms somewhat differently. On the fundamental level, it'll always help to have the most efficient algorithms. You knock off a factor of 1 million on the algorithm before you start putting on a hardware, you're already winning on any hardware. So most of our stack works like that. The higher levels of it that are very problem-oriented will do clever maths and clever insights and stuff to really, really derive a really efficient circuit for that. And then the later stages, we will implement it differently on different hardware modalities. So
and with the trapped ion gate speeds, are you also considering like what IonQ is doing right now? Their hopes of bringing that time down from their acquisitions and everything.
So before they were acquired by IonQ, we know the Oxford Ionic guys pretty well, and they have a really interesting, different. They're taking a different technology approach to, say, Quantinuum, and it's definitely interesting. The Oxford Ionics guys are really great. They need to get, in Phasecraft, we can contribute and work in partnership with harder companies in a useful way and deliver, meaningfully for them and for us once they have enough qubits for us to run something that cannot be, is beyond state vector for sure, simulation, even on GPUs, and beyond, ideally, really pushing the limits or beyond what tensor network methods can do. So with that particular modality you're talking about the kind of the thing that has the potential to speed up the gate speeds on ion trap, which is kind of, as I understand it, is the Oxford Ionics technology that they're now building up. They have to get a bit hardware that's a bit bigger before we can meaningfully kind of start stress testing it, I think. But I think, it would be great. Ion traps, the stuff you learn about, as maybe a grad student, maybe not quite undergraduate yet, atomic physics is very clean. Solid state physics is very messy. Superconducting physics is solid state physics, so it's very fast. You can do lots of gates, but there's a lot of noise. And ion traps, super clean, but slower. If you can reduce the slowdown, to sort of reduce the clock speed difference between ion traps and superconducting, that's of course naturally improves what you can do on ion traps. Yeah. We would say it's kind of apples and oranges, but they're kind of comparable at the moment, but with different pros and cons. Right now, the current ion traps, the best ones in the world, the biggest ones, and the current best superconducting, they're very different. They kind of pros and cons, and they kind of cancel each other out.
You do a lot of hybrid, obviously, as you said. And do you feel that the path forward is to make it very transparent what percentage is being done between, let's say, CPU, GPU, and QPU?
Yeah, this is always an interesting one because Shor's algorithm is a hybrid algorithm. There's a whole non-trivial. I teach it at undergrad. It's the one course I still teach at UCL because I enjoy teaching it. I teach Shor algorithm in full, including all the number theory part. Yeah, so every classical quantum algorithm, with the exception maybe of Deutsch-Jozsa, Simon's algorithm, there's a whole load of classical algorithm you run afterwards. So every quantum algorithm in the textbooks is actually hybrid.
Sure.
So it's sort of it's a question of to what degree. Where we at the really a lot of what we do, not everything, but because we're trying to get stuff to work on real hardware. If I want to get a full model of a large molecule moment onto hardware, I don't have enough qubits to even fit a full description of it yet. But you can, if you're clever, you can leverage the quantum computer to work on a much smaller number of qubits, but algorithmically do a subroutine that's not modeling the entire thing brute force. One day we'll be able to do that, and that's great. We've done a lot of work on that as well, but brought down how many qubits you need by crazy factors and number of gates by 1 million, but it's still not enough yet for the current hardware, so we have to be even cleverer. But there you're leveraging the quantum, so you're not solving the problem directly on the quantum computer, but doing a subroutine of a larger algorithm that then, in some sense, enhances, like it injects, nitro into the engine of the classical algorithm that really makes it perform even better. So a good example is that we've talked about the optimization in a bit already. That's an example of that. We use the quantum computer we break down the optimization problem that's too big to fit on the quantum computer into small pieces that you can then use the quantum computer to help do an initial kind of solution, which you then stitch together in order to warm start a classical algorithm to speed it up. So you're using the best of both at the moment. On the modeling side, it's even more kind of natural in that. Density functional theory is the workhorse of computational modeling in industry and computational chemistry. That's what's used in industry. DFT is an incredibly good algorithm. There's a reason it won a Nobel Prize. But it also gets stuff wrong. But the core thing is, it's kind of known why a DFT goes wrong sometimes. It's when there's strong electron correlation effects play a significant role in the properties. So you can call it entanglement if you're a quantum information theorist. You can call it electron correlations if you're a condensed matter physicist or a chemist, it's kind of roughly the same thing. So it's kind of understand which things where it goes wrong. The core part of DFT where it gets it wrong on say transition metal oxides is kind of known why, and it's the kind of thing that quantum computers are really good at solving, but it's not the full problem you need to solve. It's a much smaller thing that is essentially just about the electron-electron interactions. Okay, one of the things we do in our quantum-enhanced DFT algorithm, we get the quantum computer to solve that bit. And now already like 50, 100 qubits is already can do better on that to derive, to manage to get better kind of approximations to the so-called universal functional, which you then use in a DFT loop in the standard way. Again, the quantum algorithm is being used in a way that can be used now to enhance very tried and tested classical algorithms that go wrong in known ways and get rid of the part that goes wrong by using the quantum computer just for that bit. So I'm looking forward to the day when we don't have to do that. We can just brute force model an entire molecule, an entire chunk of material on a quantum computer and not need to do that kind of stuff. It'll be really interesting to see how it compares. But, we want to run things in Phasecraft now without waiting until there's large-scale fault-tolerant quantum computers, and we don't twiddle our thumbs until then.
Yeah, in classical computing right now, most things people try, they don't even slightly attempt to optimize it because the horsepower is so much ahead of what the problem is that there's no need to spend time
This is
optimizing anything.
right,
You know?
but it didn't used to be the case. We've just kind of our
course.
collective memories don't stretch back far enough. Mine, I'm not that old to it, but you know, all of that stuff was done. It's now in libraries that are either hand-coded assembly or Fortran code that no one touches anymore. It's already been done, and we use it all the time. But it was a solved problem decades ago, and from my perspective, classical computing is boring, at least the traditional algorithms, because there's a lot, it's not fully solved, but there's a lot of things that are just well understood, implemented, production ready, and we use them. Quantum computing is not like that. We're in the interesting era where the algorithm stuff makes a big difference, and you know, and then there will be as it matures, that will be, you know, Phasecraft stuff will be underlying all of this, and people and things will be built on top of it. But we're in the interesting era where we don't know how to do this optimally. We're still discovering new ways of doing things.
Yeah, any little edge is an edge right now.
Yeah,
of course. Anything you can eke out. And on that note, like when I had the guys from Iceberg Quantum on to talk about the Pinnacle architecture paper,
yeah,
one of the things that's scary about what they said is that, yeah, that 100,000 qubits to crack encryption, that's not their final word on the subject, which makes the paper a silly name. Pinnacle architecture. Nope. There's going to be another pinnacle and another pinnacle. You know, so
I mean, this is something I'm repeatedly saying is like every time someone says resource estimate, it's not a resource estimate, it's a resource upper bound.
Yeah, exactly. So
it can only get better.
Yeah, like they think they could bring it maybe down to 10,000. It's possible, you know. So I have to ask, like, how much do you see something similar happening with your other use cases? Like, do you think we're going to have these crazy, you know, order of magnitude reductions in qubit requirements?
We have already got peer-reviewed papers from 5 years ago showing you get exactly that. So yes, absolutely. We also know that that's not the end of the story. But then, you know, we also, to a large extent, we are the world experts in knowing how far you're likely to be able to push in that direction. We know we could push further, but it might not be enough to get you down to the current 100 qubits. So, okay, let's invent a new algorithm that lets us keep going in a different way and down further. And for example, you know, one like the hybrid quantum classical stuff is let's cut the problem down to the small core difficult piece and solve that on the quantum computer is kind of the philosophy instead of the whole thing. That gets you even further. And yeah, it's not, you know, you can almost the like lines of research that, you know, we've gone some way along. We know we could push this further, and it would probably get us to a certain point. But a new algorithmic idea suddenly changes the entire gradient, and we know maybe we can go to something much lower already. So, you know, quantum computers that exist now are already starting to be used for stuff that is useful scientifically. It's really just in the last year, but we're at that point. It's scientific problems, not yet commercial, but that's just that's the next step, and that's, you know, where we're heading towards. So yeah, you never know if there's going to be, it's usually in the applied research though, it's not one groundbreaking once in 20 years breakthrough. It's usually a whole load of clever smaller breakthroughs that stack, is our experience. You know, the iceberg paper is an example of that. It's not unknown ideas. It was a whole load of stuff that was well known in some ways to all the people in the field and the algorithms experts and the error correction experts. But that's not trivializing it. You got to do the hard work of putting that together and making it all, seeing if it really, each of these is isolated ideas. That's the applied side of the research, which is just as important as the kind of blue sky theory.
Yeah, I wanted to impress upon listeners that don't just read those weird estimates that people made quickly just to make a statement like, oh, 5 years away because we need, you know, 10,000 logical qubits or whatever. Like, that's just, there's a lot of nuance there, you know.
Completely. And also it's just at the mercy, it'll be obsoleted. And even everything we say, this is how many qubits you need to solve, you know, to model strontium vanadate, will probably be obsoleted by us in a year or two's time.
I hope.
It's just me too, absolutely. So it's always an upper bound. And this is the thing about algorithms and the algorithms applied to real world applications. This is the thing that brings forward the timelines in a to some extent, radical, non-predictable jumps that are different in nature to the hardware development, which is also critical. I mean, those curves have to cross, but the resource requirements curve, clever ideas can suddenly change the orders of magnitude on it in a way that the hardware development rarely has massive orders of magnitude change, unless there's an entirely new architecture that comes along out of nowhere, and which could happen, and I would love to see it happen, but probably don't want to bet on that.
And you might not know. You might publish a paper that estimates a certain number of qubits are needed to do something, and then you'll get a phone call. Oh, we have that machine.
Yeah,
So
that would be great.
Yeah, your advantage is already there.
I think we have a pretty good sense of what all of the machines that are likely to be around. So unfortunately, I think that's probably not gonna. We have to do it the hard way. But of course, I mean, it's one thing that like always people think Phasecraft is working on NISC or pre-fault tolerant or wherever the current term for it is. That's no, I would love it if a fault-tolerant scalable quantum computer arrives tomorrow. We will then just solve problems that are a million times bigger than anyone else can. We just flip out at what we do. At the moment, we use that to try and squeeze things down. As soon as you got a scalable fault-tolerant quantum computer, that factor of a million doesn't go away. It just means we can solve problems a million times bigger than anyone else. I would love to live in that world. I'm not going to bet the company on that arriving next year or in 5 years necessarily, or in 10, where you really can just ignore the resource limits and treat it like we do classically for most things as basically waste clock cycles for convenience. We've got more RAM than you can possibly, and if not, you just buy some more and put it in a cloud. Not everything in classical computers like that, but a large fraction of it is, and it's a beautiful world to live in. We don't live in that world yet quantumly, so we have to do it the hard way. But when a fault-tolerant scalable quantum computer comes along, Phasecraft is not a NIST company. We are an algorithms company. You are never going to stop caring about a factor of 1 million or 10 million improvement in your algorithm's efficiency. We still care about that classically. I mean, we care about factors of 10 classically still. We are never going to stop caring about factors of 10 million.
Yeah, no, I believe that that crisscross idea of the two lines. Yeah, I think that's going to apply to literally everything in quantum, not just encryption.
The one thing about encryption is what matters more than everyone always talks about qubit number. I think you know this very well, but it's like that's not the critical metric. It's the circuit depth or circuit size you can run. That's the more critical metric. Qubits count goes up, is easier to grow. It's not easy, but on the hardware side, there's less obstacles to increasing the number of qubits. But increasing the depth, circuit depth you can run out to, either means swallow big error correction fault tolerant overhead. But so you, even in fault tolerant era, you don't stop caring about the underlying raw fidelities, gate fidelities, because those lower your overheads on the fault tolerance. And that is the much harder thing to push out, is to how many gates or how many layers of gates can you run. That's the limiting factor. And for things like these latest results on breaking crypto systems, the number of qubits count is very low. The number of gates you need to run is lower than it was before, but it's still quite big. You still need a scalable fault-tolerant quantum computer.
And a terrifying one is the, in terms of, not terrifying because it'll work, I think terrifying to try and think of running it is the idea of, the 10,000 qubits for ECC idea. That's 9 months of runtime. Like, I just don't believe right now we can get a machine to run for 9 months.
That's right. And that's, I think, 9 months on solid state hardware as well.
Yeah.
On ion traps with a factor of 1,000.
I think it was neutral.
It might be neutral atoms,
Yeah, it was neutral atom for 9 months.
Well, it depends on which result you're talking about, because there were two, a bunch of papers. That's right.
Yeah, there was the 10,000, and then it was like 26,000 qubits for roughly a week or 10 days. Or
Indeed.
A lot more doable.
Yeah.
So I wanted to ask, is there another major like quantum myth that is circulating, and the folks you talk to who want to try and do use cases, but
there are many.
Okay, I know if you have a list.
I mean, there's still plenty of people out there who think that, like, even last week I was hearing from certain high-placed people, not in companies, in government, like, but why do we need algorithms? We just run our existing algorithms on the quantum computers and they get speed up. I'm like, really? We've done such a bad job as a field then, as people like me, educating people, because no, that's not how it works. But that one's like most people who are really, really in contact with the industry know that it's not how it works. Quantum computers function completely differently. It's a different model of computation. There's no speed up for the existing algorithms. You have to think differently. One that's quite prevalent that I hit a lot in the last few years, unsurprisingly, is, doesn't AI machine learning just obsolete all applications of quantum computing? That's not a stupid question, but on the surface level. But I think my answer to that is usually like, AI machine learning and LLMs and deep neural networks have not obsoleted the conventional classical algorithms either. If I want to model a bridge, say, to take an example I was talking about earlier, I'm not going to use an LLM or a deep learning algorithm to predict if my bridge is going to stay up, because I can just write a finite element analysis computation that's efficient, mature, and it will tell me if my bridge is going to stay up or not. I don't need to have a deep learning model guess it. So deep learning and LLMs have solved problems in computer science that were just unsolvable and intractable. We hadn't gained any traction on for decades. They haven't obsoleted the stuff that was tried and tested, solved and productionized, they solve a different class of problems extremely well that just couldn't be solved before. Quantum is exactly the same. The kind of things you can do with a quantum computer, it solves classes of problems that we do not expect an LLMs to be able to solve effectively. If I can model a material in full ab initio simulation on a quantum computer, why would I not do that? Why would I use an LLM to predict structures of materials if I can just compute it? In the same way that why would I use an LLM or a deep neural network to predict if my bridge is going to stay up? I'll just compute it. They're very complementary. So in Phasecraft, there are, if you like, I guess the way I conceptualize it, there are now 3 models of computation. There's quantum computing, there's traditional classical algorithms, and there's deep learning, LLMs, AI. These are different classes of computational structures that are useful for different things. We in Phasecraft will leverage the best of all of them. So there's stuff we do where we're using classical algorithms together with neural network deep learning, together with quantum computing, and harnessing the best of all 3. So they're complementary. They don't, the things that deep AI is good at are not the things that quantum computers are likely to be good at anyway.
Yeah, AI for quantum has been a big success. All up and down the stack. AI has helped quantum mitigation, suppression, all sorts of things, for errors.
That's right. Yeah. And it's, so this is something that's quite common. It's like, doesn't, even from like CEOs of major companies sometimes said in their speeches, like, but machine learning is just obsoleted quantum computing in all of its applications before it got off the ground. We'll see, but I doubt it.
Yeah, I doubt it.
There are just classically hard problems that, I'm a theorist originally, I'm a mathematical physicist / theoretical computer scientist. We can prove that certain classes of problems cannot be solved classically unless radical complexity class hierarchies collapse that would shock everyone and win multiple Turing Awards. We might live in that universe, almost certainly not. The question is only, amongst those things, are any of them useful in real world applications? But there's some classes of ones, like the old one of simulating quantum mechanics. It falls into that class. It's very unlikely that classical algorithms are going to solve it fully. And whereas we know provably that quantum algorithms can, we just need a big enough quantum computer. Or a better, efficient enough algorithm, which is the side we do.
Yeah, and of course the other myth is this idea that you're able to take something like ChatGPT and just run it on a quantum computer. That's the other one that drives everybody crazy.
That's just like so wrong on so many fundamental levels that it's just like, it's fair. I mean, both machine learning is non-trivial. It's got a lot of depth of, behind it. It's not a trivial area of science. Neither is quantum computing. You need technical expertise to really understand why that is a silly question to ask, and it's not to dismiss it as like, we need to educate people on that. But yeah, that's right. You can't.
There's a very popular podcast with someone who has a similar haircut to mine, and he says that almost 3 times a week, and I get so many emails every time he talks about it. So I would love to go on his show and set the record straight on that. Yeah, that'd be great. So you're using AI, like you said, it's in there.
It's a very useful tool.
Yeah, and that makes sense because, like I said, the AI for quantum thing has been a smash success. And in general, before I let you go, how could listeners or viewers get involved with what you do? Like, is there going to be some way that they can do a use case using your approaches? What's the best way that they could interact with what you've accomplished?
So for sort of end users, customers, companies, the companies who have problems they would really like to have that are things that quantum computing might potentially be good for, and they're not, nor should they have to be quantum algorithms and implementations experts when what they want to do is like they're a logistics company. They have a problem they need to solve. We work very closely with them. We like to work pretty closely with such companies and end users to work together in a more joint development type basis rather than not consultancy, where we actually dive deep into what's the problem they really need to solve, because we can bring our expertise on what quantum algorithms, how we can design application focused algorithms and implementations that solve that problem effectively. That's the one they really need and care about, not some abstract problem that you write a paper about. So we usually like working very closely with people and deeply with sort of users, customers and it's usually a sort of deep research level project, but with a very applied goal at the end. We will leverage everything we know and our stack to do that. For listeners, that's a little bit trickier. Your average listener, if they're listening to a podcast, it's hard. It's a little bit hard. I mean, follow us, and we publish most of the interesting stuff we do still in on the archive. Now, that's not maybe super approachable because they're scientific journal papers, but we also are trying. We put out stuff that's like a sort of higher level summary of those things. We very much don't hype and bullshit about quantum computing. We care about it too much. We don't promise that you should switch off all your classical computers tomorrow, because no, it's
yeah. And
so yeah,
deep researches might not even be quantum, right? Like you might find that a problem. Just there's no need to touch quantum at all.
Yeah, there's plenty of problems where I will never use a quantum computer for it.
Yeah, it absolutely just doesn't make sense. So
yeah,
that's
I mean, there's a lot of appetite for people are very interested and excited about quantum computing. It's a great thing, and that excitement is great. There's a lot of it. I can see how it's hard to get into, to understand what's true, what's not. Most of the time, there's a lot of not just us, but also a lot of people in academia who write very eloquently to the public and tell the truth about it without neither hyping it nor sort of saying it's never going to happen. And John Preskill, if you ever get a chance to hear him give a talk, is fantastic. He's very measured. He knows deeply what he's talking about. He often says nice things about Phasecraft, which I'm very, it's very flattering of him. John is great, but it's because he's a scientist through and through, and he's very good at explaining the field to other people. Scott Aronson, of course, well known for his blog, again,
sure.
Podcasts like yours, this kind of thing. I think there's a lot of excitement, and that's great. There's also a lot of nonsense peddled. It's hard to see. As a non-expert, I can see how that's quite hard to navigate. So we love talking to people. We're very, very busy on solving the difficult challenges of getting this stuff to work. But follow us. Some of our team are always. I mean, everyone on our team, you grab them somewhere at an event, at a showcase, and they're scientists and researchers and engineers. They love talking about what they do.
Yeah, and I have nice things to say about Phasecraft. That's why I did want to have you guys on. So
that's always nice to hear.
Yeah. No, I'm impressed. I hope you guys keep bringing the qubit requirements down and the performance levels up. That'd be amazing.
We're working, day and night on it. We're not done.
So yeah, Toby, thanks so much for coming on.
Oh, thanks a lot for having me. Really, it's been a pleasure.
That does it for this episode. Thanks to Toby Cubitt for joining to discuss Phasecraft. And thank you for listening. If you enjoy the show, please subscribe to Protivity's The Post-Quantum World, and maybe leave a review to help others find us. Be sure to follow me on all socials at Constant Hacker. That's Constant with a K, Hacker. You'll find links there to what we're doing in quantum computing services at Protivity. You can also DM me questions or suggestions for what you'd like to hear on the show. For more information on our quantum services, check out Protivity.com or follow Protivity Tech on X and LinkedIn. Until next time, be kind and stay quantum curious.